So today's talk is how 500 real users are worse than 3,000 bot users, and they're the story of scaling a JupyterHub instance. So I work for the NSF-DOE Vera C. Rubin Observatory, which is a mouthful to say, so henceforth that will be Rubin Observatory, or often in fact just Rubin. And we are an observatory that is located on Cerro Pachon in Chile. It's an optical band telescope. The primary tertiary mirror, it's two different curvatures on the same piece of glass, is 8.4 meters. That feeds a camera that is 3.2 gigapixels. This is both the largest single piece of glass ever constructed and the largest digital camera ever constructed that we know of. There may well be some three-letter agencies, either ours or someone else's, that have a higher resolution, but we don't know about those. This particular picture of the observatory, which is a 10-story building with the night sky rotating above it, was taken by Hernan Stockebrand, who, in addition to being a terrific astrophotographer, is one of our IT guys in Chile. So I'm just going to let some video scroll while I talk a little bit about the telescope itself. It's got a 3.5 degree field of view, which is about 7 full moons side by side. It will take a picture of the entire southern sky in one band or another every 3 days. It's got 6 optical bands ranging from the near ultraviolet to the mid-infrared. Also, the telescope mount assembly is painted very nearly this color of teal because Victor Krabendam ran the construction of the telescope, and he paints all his telescopes that color. So let that go a bit more. During the 10-year survey, we're going to be collecting 15 to 20 terabytes a night of astronomical data. The primary catalog is going to end up being about 15 petabytes, and the total data holdings, once you've got the raw images, calibrated images, some of the intermediate products, the various catalogs, is going to be on the order of 500 petabytes, that is half an exabyte, which is a lot of data. We're going to begin with survey operations, we think, towards the end of the year. We certainly hope so anyway. And if you're interested in more stuff about the observatory, you can either go to rubinobservatory.org, or on the last page of this talk, there's a link that I give to a friend's Astro 101 course, which I think is a pretty good introduction to the observatory and its capabilities for interested non-professionals. However, that's not really what I'm here to talk about, although I will point out that we're just seeing some panning and zooming of some beautiful astronomical images. These are from our first look event, which we collected a bunch of data. This is approximately half the total survey depth. This is the clarity we're going to have after about 5 years of taking pictures of the sky over and over and over and reprocessing. But we only did about half of 1% of the total field of sky we will eventually cover. Up here, this is a link to skyviewer.app, which is a pan and zoom thing with that data in it. And there's something that I would very much suggest you try, which is go to Skyviewer, pan around until you see something that looks kind of neat, zoom all the way in, pick some fuzzy blob. Congratulations, you are now probably the first and the last human to ever look at that galaxy. And that's kind of the scale of data we're talking about. To a first approximation, no one is ever going to look at any of these pictures. They're going to work with the catalog data. They're going to look at a vanishingly small sample of the images. So, moving on to the actual Jupyter relevant part of the talk, I mostly work on the Rubin Science platform, henceforth RSP, which provides hosted ad hoc analytics to the science community. And what that basically consists of are Jupyter Notebooks running a kernel that contains our entire analysis stack, the analysis stack being the thing that takes the pixel data from the sky and turns it into a catalog of objects in the universe. And then there's a search and visualization tool for the astronomical data, so you can actually look at the pictures, zoom in, pick a region of interest, pick an item of interest, whatever. API access to all the data here. and then a pile of other services. I'll talk about a couple of them later, but there are a lot of other capabilities, but they are basically in the service of we took a bunch of pictures of the sky and we turned them into a catalog of objects. So most of what I've been working on for the last 8 years while I've been at Rubin has been the notebook service. And I'm going to talk about scaling it. And there we go. So our environment is actually, it's semi-standard. It's based on 0 to JupyterHub, as most Kubernetes deployments are. But we've chosen to do some slightly different things with it. One is that we have individual user namespaces and individual user DNS domains for isolation and for ease of tearing down user environments once they're done. And our container images have to be pre-pulled because they contain the entire analysis stack, they're very, very large, on the order of 15 gigabytes uncompressed. If you do not pre-pull those, your users will get very bored and wander off while they're waiting for it to pull and spawn. And then we use a custom spawner, and this may come as a surprise to you. I don't see offhand anyone who is in for most of the inside baseball that's about, but it was our efforts that kind of pushed the individual user namespaces over the finish line. And then we did a lot of the work to convert the Kubernetes spawner from threaded to async IO. That said, we then ended up not using Kube Spawner. And the reason for that is that we're using individual user namespaces, so effectively the thing creating the Kubernetes objects has to be cluster admin. JupyterHub has a lot of other responsibilities and thus a fairly large attack surface, whereas the Spawner API is very, very small. So we have a privileged pod that runs, that does the actual Kubernetes object creation with a very small REST API, and then JupyterHub just talks to that using a custom spawner class. We have a few lab extensions doing things like adding save and quit button, a nice two-way interface between queries in the visualizer tool and creating templated notebooks from that, rather like the ESA presentation yesterday showed. And then a nice hierarchical menu of tutorials because it's a very complicated analysis stack and we provide a quite large set of here's how you use it for our new users. And then all of this is deployed with Phalanx, which is Git-driven Argo CD, effectively. We define configurations for mini sites, and those are applied through Argo, and we get an instantiated Kubernetes configuration at the end of it. So on June 30th, we had our first public release of observational data. And what I'm going to be talking about is data.lsst.cloud, which is hosted at Google, US Central 1. And I'm going to be talking about both data and its integration counterpart, which is where we actually did our scale testing because we had people using data the whole time and we couldn't take it down to do scale testing. We have many other deployments. Some are on premises. For instance, we've got one, our US data facility, which is SLAC, formerly the Stanford Linear Accelerator. We have a deployment at the Summit. We have a deployment at the base facility in La Serena, Chile, about 90 minutes from the Summit, but on the coast. But this one's only going to talk about the Google Cloud-based stuff. So we just run on Google Kubernetes Engine. We have auto-scaling enabled, and it's honestly nothing fancy. 32 core, 128 gig nodes. We can scale as many nodes as we need to. Usually we're running on the order of 7 to 10. When a whole bunch of users show up at once, we go much, much higher. And the nice thing about that is that no one is going to be able to download a 15 petabyte catalog. This has come as a shock to some of the older members of our astronomical community, but fundamentally, it's a lot easier to put the compute next to that much data than it would be to transfer any meaningful amount of data out of it. So we think that there are about 10,000 people who will ultimately be allowed to use the system. There's a whole complicated data rights story that I'm not going to get into, but all US and all Chilean astronomers are the bulk of that 10,000. That's about half the worldwide astronomical population. Of note, even though there are data rights issues and the catalog data is not immediately public, within 4 years after collection, it is world public. Absolutely anyone, regardless of whether or not they're even an astronomer, will have access to it. but they won't necessarily be able to have access through this platform. However, it's all open source. You're welcome to stand up your own instance and make arrangements for whatever subset of data you want. For Data Preview 1, or you will once it is out there and public. For Data Preview 1, we decided to set a goal of 3,000 concurrent users. We were sure that was going to be comfortably more than the actual number of people who would show up. And as it turned out, 3 months after Data Preview 1, we had about 1,500 users. Last week, I had to relocate our storage again, and we had about 1,700, which is less than 3,000, but is also, it's a fair chunk of astronomers. So our testing methodology is based on a service we wrote called Mobu, and the thing you need to know about Mobu is that it simulates an astronomer logging into the system and doing stuff. Crucially, from Jupyter's point of view, it doesn't know whether it's talking to a human or one of our bot users. It goes through the same authentication, it uses all the same API calls, it looks exactly like a human coming into the system. And so if we got to 3,000 simultaneous users, we figured we would declare victory and move on. We started towards the end of January. We did 1 3-hour run every week on Fridays, and we finished up this piece of it in late April. By the way, the scale testing and breaking things in general is really, really fun, great team activity. I wholeheartedly recommend it to anyone. So we started off, JupyterHub itself is just fine. 1,000 users in, out, not doing anything, no problem, nothing's breathing hard, nothing's sweating. 3,000 only failed because at some point we'd hard-coded a limit of 1,000 simultaneous tasks, figuring that would be plenty, and reality caught up with us a couple of years later. Once we started spawning lab pods, things did not go so great. 100, no problem. Again, everything worked exactly as expected. We tried 1,000, and around 300, we started having very serious problems, mostly timeouts and spawn failures. Some of it was that we needed to give the hub more memory, but that was not all of it. The Kubernetes control plane was not keeping up with it, and spawns were just mysteriously failing. So February and March, we spent trying to figure that out. So we found a lot of stuff in our controller, not a lot, a few things in our controller that were race conditions that we just never seen, because when you have 20 people using the system, you're not likely to trigger them, but several hundred, we did find them. We ended up having to turn down polling cadence from the lab. I'll talk about that in a minute. That was the major thing. And then we had a practice of cloning all the tutorial repositories into everybody's notebook on startup. Worked fine, and GitHub lets you clone public repositories quite freely. Turns out that they don't let you clone it infinitely freely, and at a certain point they do tell you to back off. So the first fundamental problem we hit was the JupyterHub database. There is a single database connection, and it is synchronous. When you are doing a database transaction, that blocks everything else in the hub. And each lab polls to register activity every 5 minutes, which is fine with a couple hundred users. At 3,000 users, you're looking at 10 operations a second, and we are not running a very big database. I mean, this hub session database is not complex, is not large, and frankly, we don't want to spend a lot of money on it because it's a pretty tiny state database. So what we did instead was just drastically reduce the frequency of polling, and that was fine. Because it's not a classroom situation. It's not like we're trying to get rid of everyone after every class. We let people run for about a week. And so it really doesn't matter if their lab runs for a week and 5 minutes and then is shut down, or a week and an hour. So we went to an hour, and that cut the problem by a factor of 12, which was plenty. But the single threading on the database does mean that is in some sense a fundamental limit on how far we can scale. Fortunately, JupyterHub is moving to a much more traditional database session per request model, and we intend to be very early and very enthusiastic adopters of that as soon as it's feasible to. Yes, we realize that will allow that each hub will be able to handle fewer users, but we're already running under Kubernetes. Horizontal scaling should be very easy. So some other stuff we found while we were scale testing, IBM publishes a really great repository, Jupyter Tools, which is basically about how to scale a hub. We took their initial recommendations for culling and activity polling. That got us in the right ballpark, and then we just kept tweaking until it all seemed right. Google Kubernetes Engine also imposes a 200 requests per second limit. This is apparently a fundamental and non-tweakable parameter, so at some point we would have to have multiple clusters to be able to satisfy 10,000 users. We probably will need multiple clusters, but long before that point anyway, and we will probably geographically distribute them, so European users use a European data center, Asian ones go to someplace close to them, etc. So we're not too worried about that, but it does represent a fundamental scaling limit if you're using GKE. And finally, we were pulling our images from GitHub Container Registry. Much like cloning repositories from GitHub, public container pulls have a very high rate limit, but it is not an infinitely high rate limit. However, we're inside GKE. Google provides an artifact registry, so we just moved our images and pulling from there. And as far as we can tell, Google is telling the truth that it is free within a region and there are no rate limits. At any rate, we have never hit them. So by early April, we actually were getting 3,000 simultaneous users log in, run print hello world, log out. And at that point, okay, we had some other stuff we needed to test. So we declared victory and moved on. And then the big day arrived. Well, we got about 500 people wanting to spawn, and about 300, maybe 350 succeeded, and we started seeing failures, which was unfortunate. And they were not failures we'd seen before. We did not have memory exhaustion in the proxy. We did not have memory exhaustion in the hub. Why were these failing? And that leads to the big reveal, the answer to the question posed in the title of the talk. Our bots were well behaved and logged out when they were done. Now, one of our extensions actually is a nice little save and quit without saving thing under the file menu. And it turns out that nobody actually uses that. At the very best, people will close the tab when they're done working, and usually they don't even bother to close the browser tab. They just click over to some other tab and forget about it. Back in August, configurable hub proxy v4 was still the default. Now it is version 5. As soon as we realized that it was an option to adopt version 5 early, we did. And the problem that if you leave WebSockets open, the proxy falls over at a certain point was no longer an issue. But we did not know that prior to launch day, which was kind of saddening. However, if you learn nothing else from this talk, it is use configurable hub proxy v5, but if you're using a modern 0 to JupyterHub, that's what you get by default today. So fortunately, the most painful lesson we learned has already been addressed. Since then, we haven't seen quite the same spike. Like, everybody wanted to jump on the first day things were available, but we've seen 350 people at once, all doing useful work with no apparent problems. So we learned some other interesting things after data preview 1. We had a set of notebooks that validated data access basically by selecting a bunch of columns from the database and running that in a tight loop because we wanted to make sure that database access was sufficiently performant. Well, it was, but we had a pre-configured overcommittal ratio of about 4 to 1 in terms of hub requests to limit in Kubernetes, which is fine for normal use because most users spend most of their time looking at the screen wondering what they're going to do next. Unfortunately, our test cases just run in a tight loop over and over and over, and they quickly got to their pod memory. No one was asking for more than the 16 gigs we gave them, but given that the nodes were scaled, assuming that they'd be using less than that, but more than 4, we would run out of node memory and then start evicting our database users. So we made the overcommittal ratio tunable. in case we are doing effectively entirely testing users. And most of the remaining bottlenecks we found are neither in the hub nor in the lab, but in some of the intermediate services. And I'll talk about that here. So almost certainly you're not just running JupyterHub plus notebooks, right? You have some sort of authentication and authorization system to see if someone's allowed to use it. And then those notebooks almost certainly are querying some data source, right? So some of those, and it may not, your usage patterns may not go directly from your notebook to your data source. For instance, one of the things we provide is a cutout service, which says, I'm interested in this object, please give me a small piece of sky around it and show me what else is there. This turns out to be moderately computationally intensive, and we'll get to that. We are using a thing called Gefilfer, which is King Arthur's gatekeeper. And what it does is it basically manages ingress to the various components of the system. So we can enforce rate limits in it, and we can enforce through scoped OAuth tokens whether or not that particular service is something the particular user is allowed to do. And if you're running a service like this, you are probably going to need to do something like that. Gefilfer and all of our stuff is available under the MIT license. Please feel free to use it for inspiration, or if it actually fits your use case, just use it as is. So I'd like to talk about some challenging uses of our system. Number one, people tried to mine crypto. Now, we give them at most 4 CPUs, no GPU. So they may have made as much as dozens of pennies. It also turns out that Google is really good at recognizing this, and we got some notices saying, hey, you might want to check out the following workloads because they're making some real suspicious outbound calls. So, you know, don't try it at home, kids. Other outlier users, well, somebody wanted to build a training set. So they were lawnmowering through every single object and doing a cutout of it and getting its characteristics and building themselves a set, which is great, except the cutout service itself eats a lot of resources, and we were starving out other users because this one user was just methodically working their way through the entire pretty large result set. We first tried to just rate limit use of the cutout service, and that turned out to be the wrong thing. So you need to think about what it is you're actually rate limiting. The reason it's the wrong thing is that you actually want users who are doing small, fast queries that want a few columns of your database, not a select star, and they can and should do a bunch of those very fast. So it turned out for us it was the number of concurrent queries in flight that was a better metric for is this going to be a problem than just how many queries are you doing. The other thing we learned was that if you are using persistent storage, which we are, and Yuvi talked about this yesterday, you absolutely 100% need to quota that storage. We actually ended up doing a slightly different thing than Yuvi, but effectively what we are using traditional NFS quotas. Before we imposed them, we had one user who was using as much storage as our other 1,000 all put together. That user had to discard 99.5% of the files that they had amassed, and that was not a happy experience for them, though it was a happy experience for the rest of us. So to summarize, here's what we learned, and if you too are trying to run a JupyterHub implementation at scale, these are things you probably need to know as well. Number one, use configurable hub proxy 5, not 4. Fortunately, that's now the default, so you don't have to do anything special to do that. Number two, if you can reduce your database polling frequency, you probably are going to want to at least until the hub can be horizontally scaled and can use a request per session. Then your internal resource usage, in rough order of importance, again, your persistent storage, which is certainly our dominant cost factor. Our POSIX storage is costing us more than our compute and memory right now. Your CPU and memory is second, and then any resource-intensive internal services need to be considered as well. Finally, have some plan in place for offboarding people quickly or rate limiting them quickly, because you want to know what you're going to do before it becomes an issue, and it probably will become an issue. And the last point is something that if you come to this, as I did, through system administration, is going to seem quite obvious. And if you're coming to this from a development perspective, maybe a lot less obvious, which is there are times when you're going to have to make some people fairly unhappy in order to keep everybody else reasonably happy. And yeah, sorry for those people, but the overall health of the service is something you need to preserve, even if someone is not getting the results they want as quickly as they want. And that's about it. These links, feel free to follow them. They're all also in the PDF. The general talk, I think, is quite good, but then I'm biased. And Rubin key numbers is not just the 15 terabytes a night, 15 petabytes by the end of the survey, but a whole bunch of other really mind-blowing numbers about just how much stuff we're looking at on the sky. So thank you very much, and if there is time for questions, I will happily take them. Thanks. Yes, back there.
Different sets of images when you say you support for the average user on the cluster. We were mentioning an issue with rate limits with Thornton. Have we also considered just like pre-pulling them onto the nodes, or too many for that?
I'm sorry, let me get a mic to you because I could not hear all of that. Okay.
So we've had a similar issue on our cluster where we were running into GHCR rate limits, and we solved that by adding a pre-puller to all of our nodes. Do you have too many images for something like that to work, or?
We do pre-pull. Our spawner menu generally gives you a recommended image, a couple of release images, and then recent daily and weeklies. And all of those are pre-pulled, so those come up quickly. But even when you do that, because we have pull policy always, because tags are not immutable, it still does go up and do ahead to figure out if it's got the most recent image, which is why we're still, as far as GitHub is concerned, pulling all of those images each time. It's just that the pre-puller is caching them on the nodes until the node storage is exhausted and they roll off. So we are still doing the pull from the perspective of the registry. And I guess we could re-architect it to actually ask the nodes, do you have this? But we haven't. And so far, by moving to Google Artifact Registry, it's worked fine.
Yeah, it seems like a great solution to that problem, so thank you.
Yes.
Hi, great talk. So I have two comments. They are questions, I promise. So my first question is around the simulation steps you've taken to simulate user workloads. It seems like everyone who's doing JupyterHub has the same need for that. And I took a look at the IBM repository, and I think it's 5 years old since the last contributions. And I know that we're doing simulation. We also want to simulate workloads like running NB Git puller or other sort of secondary workloads. Did you struggle with that process in terms of the state of things? Did you do additional development work to build that out? That's question one, but I'll pause there maybe.
Okay, I mean, sort of. We have Mobu is not listed there, but it's LSST2/Mobu, which, I mean, it mostly is designed for notebooks. It can either run step-by-step Python or it can run notebook at a time. So that we just simulate a user running a notebook for that. I mean, figuring out the whole flow within the hub and when you change XSRF tokens, all that was fiddly, but it wasn't that bad. And like, if you need an automated client, feel free to steal ours. 1 minute, okay, let's have the second.
Well, if anyone else has a question, they can go. I've already had one, but.
Okay, anyone? Yes. Oh, we're using Postgres. Really, here we're using Cloud SQL, but we're using the Postgres flavor of Cloud SQL. However, while this is at Google, there is nothing tying this to Google. All of this is provider agnostic, as long as you've got Kubernetes control plane that we have admin on, as long as you have a POSIX file store, we're using NFS, don't have to, and as long as you've got a Postgres database, we can do it anywhere. And we have done it at AWS, we've done it on-prem, we've done it on different on-prem, on Rancher, etc. And I think that's about out of time, so thank you very much. Thanks for coming.